Reaction mechanisms. These are the in-between steps from going from your reactants to your products. So what is it, the mechanism? It's a series of steps. If we look at nitrogen dioxide plus carbon monoxide, the products are NO and CO2, but a lot happens in between. Doesn't go directly. From experimentation, they know the rate law is an overall second-order reaction with respect to nitrogen dioxide. So this is just one graph to help you visualize it. You have your carbon monoxide and your nitrogen dioxide. An activated complex is just one that occurs during the reaction. It's when the molecules stick together. And then overall, we have carbon dioxide and nitrogen monoxide. This does not show the reaction mechanism. It happens in between the reactants to the products. So one proposed reaction mechanism is that you have your two nitrogen dioxides. They collide and they form your nitrogen trioxide and nitrogen monoxide. Once you have that available, nitrogen trioxide, it actually reacts with the carbon monoxide to create more nitrogen dioxide and your product, carbon dioxide. So scientists make their best guess at what would be a logical reaction mechanism. So we call NO3. Notice it's on the product side and then it's on the reactant side, but it's not in the overall reaction. We call that an intermediate. It's there, but then it disappears. So it's a species formed and consumed during the reaction. This is just a particulate diagram for you to see what's going on. Again, I just want to emphasize the formation of nitrogen trioxide. It's an intermediate product. It forms and then is consumed during the reaction. An elementary step we saw with our last lecture, it's one whose law can be written from its molecularity. So that's one that can be written directly from the equation. So you need to know the elementary step. The molecularity is the species that must collide to produce that reaction by that step. So you might remember we have unimolecular, bimolecular, and termolecular. For a reaction mechanism to be verified, it has to satisfy two conditions. The sum of the elementary steps must give the overall balanced equation for the reaction, and the mechanism must agree with the experimentally determined rate law. Let's see if this adds up to our balanced equation. So notice NO3 is formed and then consumed. Notice that NO2 will cancel. So we have NO2 plus CO yields NO and carbon dioxide, which is our balanced equation that was given initially. So this verifies that this proposed reaction mechanism is viable. Our rate determining step is the one that is the slowest. You can always only go as fast as your slowest step. So experimentation has shown that the nitrogen dioxide reacting with itself is the slow step, and the nitrogen trioxide with the carbon monoxide is the fast step. So the rate determining step is where we use that molecularity to determine the rate law. So if we use this guy, we have rate is equal to K, and we can use molecularity, so we can say NO2 to the second power, which is the rate law. So this verifies that our reaction mechanism is viable. So once more, we have a bimolecular slow step. So our rate law is K1 is just because we have different rates. We have two reactions. The molecularity will determine the rate law, and that rate law should give us the overall rate law for the reaction. So an example, we have an equation with nitrogen dioxide and fluorine gas reacting, and this is what they found for the experimentally determined rate law, is that it's NO2 to the first and F2 to the first. So they're both first order with respect to themselves, but overall the reaction order is second order. So the proposed mechanism is the slow step is NO2 with the F2. It forms our product, but we get an atom of fluorine there, which is consumed in the fast step. So you're asked, is it an acceptable mechanism, and does it satisfy those two requirements? So remember the two requirement. One, when you add those two steps together, they need to give you the overall balanced equation. So looking at that, notice that we have the atom of fluorine cancel out. So we have two NO2s plus the fluorine gas to give us two of the product, 2NO2F. So this verifies that the proposed mechanisms do give you the balanced equation, so it's a viable proposal. The second requirement, does the molecularity of the slowest step agree with the overall rate law? So if we write the rate law from our slowest step, we have rate equals K, and remember you can just do it from the balanced equation. So NO2 to the first and F2 to the first, which is the proposed or experimentally determined rate law. So it does verify both requirements. A reminder about the intermediate. The intermediate is one that is produced and then consumed in the reaction. So it's plain old atomic F. That's it.